Now I'd like to have a brief look at the role of architecture in the software development lifecycle, and in many ways the life cycle of the entire system. Now there is a life cycle, and although if you ever try to explain a life cycle, inevitably you will draw some sort of a sequence, because there are some things you need to do before you do other things, and this is routinely interpreted as you do all of that before you start any of this. That's not true. It's more like some sort of an animal that grows a little bit here and then grows a little bit there and grows a little bit there, and while that's going on there's another bit of this growing up, so that the thing does grow all over all at the same time, but in little lumps. Now, typically for software development systems we do have to have some sort of a concept to begin with, and we need to get some of the requirements coming out of that concept, otherwise you really don't know what to do. And as soon as we have some of the requirements, preferably identify the major requirements, we can start working on the architecture. Now the more we know about the problem and can explore possible solutions, the better. But certainly we can't start any form of architecture until we have some sort of requirements. Following the architecture, or sufficient of it to guide the construction, we can start the construction, and we can then develop the thing and deliver it. Now the note there on the slide is that architecture does play a vital role in the life cycle of software development, and the biggest mistake is thinking that you don't need to spend the time on any of the design and that you can work it out as you go. It really is a big mistake, because invariably you can't. Well, let's put it this way, people do, but the system that results is a tumble down shack of a thing that never really works properly. Now in the lifetime of a system, although a lot of the glamour and the attention is paid to the development side of things, most software systems spend about 80% of their life in maintenance mode, and 80% of the code that's written for a system is done in maintenance mode. Now doesn't this tell you something about where you should spend some effort, or where you should concentrate the attributes of the system? It's in maintenance. That's where it matters. That's where a lot of the money is going to be spent. So please think about that when you're developing a system. Maintenance, or the maintainability of a system, is seldom a characteristic that comes to the fore, but it is where most of the money is spent. So please try and think about the maintainability of the system at the time you're designing it. So examples of the maintenance type of thing is that you build a system and it works. It works all right. But now you need to speed it up from 20 transactions a second to 200 transactions a second, or 10 transactions a second to 200 transactions a second. That's an increase of 10 to 20 times. Now that's probably not achievable if you didn't design the thing in such a fashion as it can be scaled. And there are ways of incorporating scaling of the thing. But if you didn't put that in, now you've got a problem, because you're unlikely to find a CPU that's 10 times faster, especially if you're already using pretty much up the top end of it all. Another example of maintainability, system working pretty well, but the world moves on after 5 years or so, and interface tools and the way things get used change, and suddenly it strikes a combination of circumstances in which it crashes. Now the betting is that if it's crashed once due to changing circumstances, those circumstances will occur again. So it's going to crash again. Alright, you can fix the bug. Maybe. Was this system written to make it reasonably easy to find a bug, to fix the bug, to modify the system, to re-implement it, to build it and redeploy it? If it wasn't, you're in trouble. Where do we get into trouble? this is the usual question of something has happened, let's investigate and find the cause. And what we usually want to do is to find a single cause. Oh, this person did that or didn't do that, and that was the cause. This is not the case. In problems that arise with systems of that nature, that is, we can't speed it up, or we can't maintain it, or it's really difficult to maintain, there isn't a single cause. It's a systemic outgrowth of behaviors that we indulged in during the development. And that systemic behavior is usually failing to transition from programmer to software engineer. Programmers simply write things and try to work it out as they go. Software engineers do a certain amount of planning and forethought before they commit to doing much of the work. That is not always possible, and there is always this enormous temptation that I'll need to write some code to figure out how it works, and then we can put it all together. True. Now this is called muddle through. You muddle through the problem, just by doing something, see what happens, and then doing something more and see what happens, and eventually you steer it toward the end. It's a very common approach in programming, and it's a very dangerous approach because things happen. The system kind of grows, and you get what you get. You only get the characteristics you want by accident, not by design. We'd rather have them by design. Unfortunately, the recent use of agile methods seems to have encouraged people to pretty much adopt this muddle-through approach. This whole idea that we shouldn't have a big design up front, and I agree, you shouldn't invest an enormous amount of money and time in doing the big design. But that doesn't mean you should do no design. It just means you shouldn't do a big design. An absolute lack of design is not desirable either. And agile methods do seem to encourage people to muddle through all the time. And this, I think, is a bit of a problem. Bear in mind, agile software development was promoted by very experienced software developers. Those boys, if you go around and investigate every one of them, I think there were, 10 in the room or 20 in the room at the time, these were very experienced, very good people. They knew what they were doing. They assumed a certain level of professionalism in order to go into agile software development. And if you haven't got that level of professionalism, just be very careful what you're doing. Our creations are more complex than we can imagine. They require more precision than we're accustomed to. And they're more complex than we can reason about without externalizing them in some fashion. Very few of us have got the mental capacity to manipulate in our minds something quite so big and complicated as the average software system. We usually have to express it in some way so that we can look at pieces of it and manipulate that externally. This is what an architecture gives you. So in summary then, the role of architecture, or the role of writing an architecture in a software system is pretty much, it's early in the life cycle. It is important. It's not important to do it all perfectly or all of it, but it is necessary to do enough of it to get the main structure of the system put in place so that it is at least sound and will hold itself together for quite a long time. And bearing in mind that all software systems spend about 80% of their life in maintenance mode, then you really ought to try and design them to be maintained probably more than you currently do. Now, I do acknowledge there are circumstances where maintenance does take a back seat, but I'd encourage you to think of its importance. Now, we get into trouble a bit when we think of architecture as some irritation that stops us getting to the cool stuff of writing code. Well, all planning is a bit like that, but all planning is necessary as well, and architecture is a form of planning.